In the present segment, we will take another problem on axial loading, but here the difference is that the force which is acting axially, it's not a constant force, but it's varying along the length. Okay? So the problem goes like this. There is a rod of length L, this green color one. Okay, so this is that rod, okay, whose area of cross section may be S, and it's lying on a horizontal frictionless surface and is rotating about this axis at an angular velocity of omega. Okay. Now its mass is m, the total mass of the rod is m, and we have to figure out the variation of the stress or the along tension along this axis x or r. We can tell that, okay, if we take r to be the coordinate from this point of rotation, then as a function of r we need to figure out the tension, the way it varies, and the total elongation of this rod. Now for that, what we will do is we will take a small segment here at a distance r, okay, um, of length, say dr. So this is the length which we are talking about, and if we draw the free body diagram of that particular length dr, so we can see that, suppose this is the tension at T at R, and here it's say T plus dt. Okay, we don't know how it's going to change. Intuition says that T will be more than T plus del T. Yeah, let's see. Then the centrifugal force is actually acting here, and that will be say dm omega square and r. Okay, so dm times omega square times r. Now so writing the equation of equilibrium, we can say that, okay, so now the t minus t plus dt, so right, dt is equal to this dm omega square and r. Now but this dm can be written in terms of this full mass m and the length L, right? So this is like m over L times dr. This is dm times omega square times r. Okay, and then this side it will become minus dt. So that's what I was talking about. So there is a decrease in tension as we go in the increasing direction of r. So that means we can write that, okay, minus dt is equal to m omega square over L r dr. But now to find out the a function of this tension, so what we can do is we can integrate it from say t to 0. Let's do that. So if I integrate it from t to 0, because at the end, at this open end, the tension has to be 0, so because there is no force acting there, so at here the t is equal to 0, and this one I'll put from 0 or r to L, sorry. So sorry, this one will be from r to L. So so this tells us that at r, so T is the tension at so how should I write it? So T is the tension at a distance r from the center. And when we go to the R is equal to L, the tension is 0. So that's how we will figure out the dependence of the tension T as a function of R. So if we perform this integration, we will find out that T will be given by m omega square over L times L square minus R square over 2, or in a better way we can write is m omega square L over 2 times 1 minus R square over L square. Okay. So this is the variation of T with respect to the distance R from the center. Now to figure out the total elongation, what we need to do is suppose this small elemental length is elongated by the small distance, and this distance is say d eta. Okay, that means now we can say that this d eta will be equal to the stress which is existing at that point, at a point say R, over the Young's modulus of the material times the total length, right? So this is dr. Okay, so so that's how we will get the elongation of that small elemental length, and this sigma is nothing but T as a function of R over say S, the area of cross section, times E times dr. Okay, then in place of T now we can substitute this value, so it will come here m omega square L over 2 SE, and here it's 1 minus R square over L square, then dr. Now if this is the small change in the elongation, we just have to integrate this to get the total elongation eta is integration of this d eta. Okay, now so that will be integration of this whole expression. I'll take the all the constant terms out, say m omega square L over 2 times S times E, and integral of 1 minus R square over L square dr, that is from 0 to L, because we are talking about the total elongation here. Okay, now if we evaluate this, what we will get is so m omega square L over 2 SE times 2 times L over 3. Okay, so that's what we will get. Yeah, so that means eta will be so m omega square L square over 3 SE. So that's our expression for the total elongation. Okay, now and then this kind of problems can be there. For example, could have been in a very different way also. We could have stopped this end instead of rotating like this. We could have stopped this end, and the whole thing can be rotated, this end being open and this end being stopped by some constraint. Then the whole thing will be under compression, and all the stresses, the maximum stress will be at this end, and this end would have been the completely free end. Yeah, so then similar problems you can solve by suppose you are talking about a elongation under its own weight. So such cases also can be solved in this similar way. So see you in a next segment with another problem.